All right, we are about to begin Ralston Valley High School's AP Chemistry Lecture Series, Chapter 4, Lecture number 4. This lecture covers chemical reactions, in particular, oxidation reduction or redox reactions. Let's get started. So the class of reaction we're going to look at in this particular lecture is an oxidation reduction, or sometimes abbreviated a redox reaction. Redox reactions cover a wide variety of different types of familiar reactions that also might be classified as other sorts of reactions as well. In particular, something like a single replacement reaction. An example there would be the reaction between zinc metal and copper 2 chloride that there's an image on the right-hand side of your screen there. That single replacement reaction, in addition to being a single replacement reaction, is also an oxidation reduction reaction. Combustion reactions are also oxidation reduction reactions. So this redox reaction covers a wide variety of other classifications of reactions that you are all familiar with. In particular, what defines an oxidation reduction reaction as such is that there involves a transfer of electrons during an oxidation reduction reaction. In particular, an oxidation refers to a step in which we observe a loss of electrons from a chemical species, and a reduction refers to a step in which there is a gain of electrons. Now, because electrons are particles that are essentially conserved in chemical reactions, we don't see electrons created or destroyed during these chemical changes. So really, redox reactions happen in tandem. That is, if one thing is oxidized and gives up its electrons, something else is going to be reduced as it gains those electrons. One easy way to remember oxidation reduction reactions is a phrase we will refer to here, which is Leo says grr. So think of Leo the lion saying grr as he roars at something. And we remember that because it means LEO is loss of electrons, stands for oxidation. Gain of electrons is a reduction. So there's the GER for grr. Now, to have a look at a simple oxidation reduction reaction, let's look at that single replacement reaction that we discussed moments ago. In example number 1 right here, we're going to ask you to write the ionic and net ionic equation for the reaction between zinc metal and an aqueous solution of copper 2 chloride, again, which is pictured in the image above and to the right here. And we've given you already the molecular equation for that particular reaction, which is solid zinc reacts to copper 2 chloride to form solid copper and an aqueous solution of zinc chloride. Now, to write an ionic equation, all we need to do is to recognize that soluble species in solution will dissociate if they're ionic compounds, and as such, because we've got an aqueous solution of copper 2 chloride and an aqueous solution of zinc 2 chloride, which are present in the equation written here, we just need to go ahead and dissociate those aqueous species as we write our ionic equation. So let's rewrite now as an ionic equation. We have our zinc solid, and I'm going to abbreviate that as Zn with a little 0 up above, showing that it is zinc in its elemental state. That is not a zinc ion. It has no net charge. And then the copper 2 chloride is going to dissociate in aqueous solution into a copper 2 ion, Cu2 positive, and 2 chloride ions, Cl1 negative. And then on our product side, we've got our solid metallic copper, Cu, and I'm going to go ahead and notate that again as Cu with a little 0 symbol up above there, recognizing it has 0 net charge. It's metallic elemental copper. And then we've got our zinc ion, Zn2 positive, and 2 chloride ions, Cl negative. So we've now disassociated those aqueous species in writing the ionic equation. All that remains to get to our net ionic equation is to cancel out our spectator ions, which in this case are those chloride ions, Cl negative, so we'll cancel those off of both sides, leaving us now with our net ionic equation, Zn elemental plus a Cu2 positive copper 2 ion forms copper elemental and Zn2 positive, the zinc ion. Now that we've written that net ionic equation, it's really easy here to now see why this is going to be classified as a redox reaction. Take a look first at our zinc. Before the reaction occurred, we had zinc metal with 0 net charge, that was elemental zinc. And on the product side, we have a zinc ion with a +2 charge, which means to go from a charge of 0 to a charge of +2, zinc has become more positive by losing 2 negatively charged electrons. So I'm going to go ahead and label that as zinc has lost 2 electrons there, which implies, therefore, zinc was oxidized. Again, Leo says Ger, a loss of electrons is an oxidation. Similarly, have a look at my copper 2 ion that I started with there. It started off with a +2 charge, and at the end of the reaction, we had elemental copper with 0 net charge. That is, copper went from a charge of +2 down to a 0 charge, which is where we get that name reduction. We saw a reduction in the charge on that copper ion. And as such, it became more negative by gaining electrons. So we see Leo says Ger, a gain of 2 electrons, means that the copper 2 ion in this reaction was reduced. So again, we see a transfer of electrons here, which means that single replacement reaction, in addition to being single replacement, also counts as a redox reaction. Now, in order to fully understand and help us balance redox reactions, we're going to have to make use of an accounting tool, which is referred to as an oxidation state. You probably remember last year seeing those oxidation states because they're those little tiny numbers up above the symbols on your periodic table that we used to help us in nomenclature during our introduction to chemistry last year. Here in AP Chemistry, we're going to use those oxidation states essentially as an accounting tool for keeping track of where electrons are in an atom or molecule or ionic species. And by keeping track of where those electrons are, it's going to allow us to figure out what's gaining electrons and what's losing electrons so we can help to use those transfer of electrons to help balance these chemical equations. So to define more definitively here an oxidation state, we're going to call an oxidation state as being the imaginary charge an atom would have if it shared electrons in bonds equally with other identical atoms, that is, atoms with the same chemical identity as themselves. And if instead of sharing those electrons in covalent bonds, if we assigned all of those electrons in a covalent bond to the more electronegative atom if we've got a bond between 2 different atoms. So kind of an easier way of thinking of that is we're just going to go ahead and call an oxidation state as essentially a comparison of how many electrons are assigned to an atom in a chemical species versus how many electrons that atom would have in its neutral native state. So again, it's not really a real thing. It's an imaginary way we keep track of where these electrons really are. Because remember, in a covalent bond, the electrons don't just belong to the more electronegative atom. They're shared between those two. It might be a polar bond, but they're still shared between the 2 atoms involved in the bond. But for the purpose of oxidation states and essentially our accounting method here, we're just going to treat them as if the more electronegative atom was holding on to them, and that would give that more electronegative atom a more negative oxidation state. So we're going to use these oxidation states as a means of keeping track of where these electrons are going during redox reactions. So now that we have defined an oxidation state, let's go about talking about how we can assign oxidation numbers to different atoms, because it's not just as simple as looking them up on your periodic table. First and foremost, rule number 1 here says that all elements in their native state have an oxidation number of 0. And that should make sense given our definition, because remember, an oxidation state is essentially a reflection of how many electrons are assigned to an atom in comparison to how many they would have in their native state. Because these elements are in their native state in this instance, that means they have the exactly same number, so there's no difference there, which means we give them an oxidation number of 0. Rule number 2 here says that a monoatomic ion, that is a single atom that has a charge, or a neutral atom has an oxidation number equal to its charge. So for example, if I gave you a sodium ion and a 1 positive, that would have an oxidation number equal to its charge, which in that case would be 1 positive. And right now it looks a whole lot like those oxidation numbers seem very similar to charge, but they're not entirely interchangeable, and we'll see why in a couple of moments here. Rule number 3 says the sum of the oxidation numbers of all atoms in a species must equal the net charge on that species. Now, because the net charge on any molecule is 0, that means that the sum of the oxidation numbers of all atoms in a molecule must always equal 0. But if you have a polyatomic ion, then the sum of the oxidation numbers of all the atoms in the ion must equal the charge on that polyatomic ion. So for example, the carbonate ion, CO3 2 negative, the sum of the oxidation numbers in CO3 2 negative of all the atoms present there must equal -2, that is equal to the charge on the carbonate ion. Now, a couple of other tricks here. The oxidation number of oxygen is almost always -2. The reason why that's the case is, again, oxygen is the second most electronegative atom on the periodic table and the most common highly electronegative atom we're going to come across. Which means essentially, if oxygen is going to be forming bonds with other species, oxygen is almost always going to be the more electronegative species, which means it's going to get the electrons it needs to fill its octet. Which essentially means, yep, we're going to assign oxygen a -2 oxidation state. Now there's one particular example that is a counterexample here we have to watch out for, which is the peroxide polyatomic ion. Recall the peroxide ion is an O2 ion which has a -2 charge. And by rule number 3, we know the sum of the oxidation numbers of all atoms in that species must equal the charge, which means the sum of the oxidation numbers must equal -2 in that peroxide ion. Because there are 2 oxygen atoms in the peroxide ion, that implies, therefore, each of the oxygens must have an oxidation number of -1 in the peroxide ion in particular. Places to watch out for peroxides, they're almost always going to be encountered as a group 1 element plus oxygen in a 2-to-2 ratio. So like hydrogen peroxide is H2O2, or lithium peroxide would be Li2O2. So watch out for those peroxides. They will show up frequently in redox problems. And last big rule here, rule number 5 says hydrogen has an oxidation number of +1 unless it is in a hydride. A hydride is a compound in which hydrogen is bonded directly to a metal, essentially hydrogen as an anion in that instance. If it is in a hydride, we would expect to see the oxidation number for hydrogen to be -1. Now, those are kind of the big main rules. Sometimes you're going to have to kind of work your way through a little bit of more of a complex thought to get to an answer here. But in general, again, if none of these rules apply, always kind of fall back on the idea that if you have to assign a more negative oxidation state, you should assign the more negative oxidation state to the more electronegative atom. So, with that, let's go ahead and have a look now at example number 2. We're going to assign oxidation numbers to all of the atoms in each of the following species. And we'll start on the left-hand side over here with NaBr, that is sodium bromide. Sodium bromide here is an ionic compound, and because there is no net charge on the sodium bromide compound here, we know, therefore, the sum of the oxidation states has to equal 0. Within the compound sodium bromide, because this is an ionic compound, I know that there are sodium ions present and bromide ions present, which means I can use my periodic table usefully here to recognize that I know this charge on a sodium ion as a group 1 alkali metal must be +1. And by rule number 2, we know that all monoatomic ions have an oxidation number equal to their charge, which means the oxidation state of sodium here is +1. And likewise, by that same logic, the oxidation state of the bromide ion is equal to its charge of -1. So there you go. Now, have a look at our second species here. This is CCl4, a molecule we refer to as carbon tetrachloride. Now, carbon tetrachloride, unlike sodium bromide, is a covalently bonded species. So I know in this instance, I'm not going to simply be able to go through and assign oxidation numbers equal to the charge on the ions because there are not ions present here. So instead, I'm going to fall back on that idea that we're going to assign a more negative oxidation state to the more electronegative element, which in this case is that chlorine. Now, because chlorine has a tendency to gain 1 electron to fulfill its octet, I'm essentially going to assign here an oxidation state to chlorine here of a -1. And with a -1 oxidation state on each of the 4 chlorines, that means that the carbon, in order to give a sum of the oxidation states of all species here equal to 0, the carbon must have an oxidation state of +4. So that my 1 + 4 carbon balances out the 4 - 1 chlorines. Now be very, very careful here, guys. Remember, that is not a charge that we're talking about here, because again, this is a covalently bonded compound. These are not ions. So oxidation number and charge are not the same thing in all instances. So again, carbon in a +4 oxidation state, chlorine in a -1. The next one here is very friendly. I've got the Fe3 positive ion. Fe3 positive is a monoatomic ion, and as such, by rule number 2, I know that it must have an oxidation number equal to its charge, which means the oxidation state of the ferric ion is +3. Moving on to our next one here. This one right here, CH3OH, that is a organic molecule we refer to as methanol. Methanol here, another covalently bonded species. So let's go ahead now and assign our oxidation numbers. And starting with rules number 4 and 5 right here is probably going to be the easiest way to go. I know that oxygen is the most electronegative thing here, so I'm going to go ahead and assign it an oxidation number of -2. And likewise, those hydrogens, because this is not a hydride, are going to get an oxidation number of +1. So if I have 4 +1 hydrogens and 1 -2 oxygen, the current sum of those oxidation numbers is equal to +2, which implies, therefore, in order to fulfill rule number 3, that the sum of all the oxidation numbers on atoms in this species have to equal 0, because this is a molecular species with no net charge. That would imply, therefore, that the oxidation number on my carbon atom in this instance has to be -2, such that my 1 -2 carbon plus 4 +1 hydrogens plus 1 -2 oxygen, the sum of all of those oxidation numbers equals 0. So that one's a little bit trickier here. Let's have a look now at our next one, which is PO43-, the phosphate anion. This is, again, a polyatomic anion, which means we're starting here with rule number 3, which says the sum of all the oxidation numbers of the species here must equal the charge overall on my ion, which is -3. And as such, we'll go ahead and next look at rule number 4. I've got oxygen again here, which means the oxygen is in a -2 oxidation state, because this is, again, not a peroxide. So if I have 4 -2 oxygens, that is a total of -8. And I need the sum of all the oxidation numbers to equal -3, equal to the charge on the ion, which means phosphorus, therefore, must in this instance be in an oxidation state of +5. So my 1 + 5 and 4 -2s sums up to my -3 overall sum of the oxidation states. And one more, last but not least, molecular Br2. Be very, very careful here, guys. People all the time tend to accidentally throw a -1 oxidation state on here because they just get used to giving elements oxidation states equal to the charge on a monoatomic ion. But this is not a monoatomic ion. This is molecular bromine. This is an element in its native state, which implies, therefore, the oxidation state of elemental bromine is 0 by rule number 1. So now that we've had a look at oxidation states and how to assign them, we can use this as a tool now in order to help us balance redox reactions. And on the next slide, we'll talk about how to go about that process. All right, it's balancing equations time. And I know what you're thinking right now. I've balanced equations for years, since middle school probably. I don't have to worry about this, easy peasy. Well, unfortunately here, we have run into some difficulty. The rules for balancing redox reactions are much, much more complicated than they are for balancing a regular chemical equation. And the reason why in particular here is because many of these redox reactions we're going to be dealing with occur within aqueous solutions. And because these redox reactions often occur within aqueous solutions, that means that we're going to kind of essentially cheat in some instances by using other components of the solution to help us balance our equations. So when you think about what I mean by other components of the solution, think about any aqueous solution. Obviously, there's going to be water present there, which means water can act as a reactant or as a product of these chemical reactions. And even more beyond that, because of your familiarity from last year with some of the properties of water, in particular, that water tends to, through autoionization, form both hydrogen ions and hydroxide ions. Depending upon the acidity of the solution, I'll also have those species present as well to help me balance these equations, because those species are, again, chemically reactive species. So essentially, our steps for balancing redox reactions here are going to make use of the fact that we can pull from the solution itself in order to help balance and make these things work out. So we'll run through the steps here real quick here. Reading the steps in and of themselves is not super useful. It's more important going to be to just have a look at how we apply these steps on a couple of example problems coming up after here. But we'll still have a quick look here through the steps. So step number 1. assign oxidation numbers. On our last slide, we went through the process of how to do that. You should get plenty of practice on assigning those oxidation numbers. That is the very first step. Step number 2, once you've assigned oxidation numbers, we're going to be looking for what was oxidized and what was reduced. And again, we're going to remember our device for remembering oxidation and reduction is Leo the lion says grr. Losing electrons is an oxidation, gaining electrons is a reduction. So essentially, here we're looking for changes in oxidation state. There's always going to be one thing getting oxidized and one thing getting reduced, so make sure we pay attention. Step number 3, we're now going to separate our chemical equation into what we refer to as 2 half reactions, one describing only the oxidation step in isolation and one describing only the reduction. And after that, we move into what we call a sequence of balancing. It is incredibly important that we throw out creativity in this instance. When you go into your sequence of balancing, the order in which you balance things is incredibly important. And if you go out of order, things are going to get into a tangled mess and then things are going to end poorly. So the sequence of balancing always begins first with the atoms that were oxidized or reduced. And put a star in your notes here, guys. This next step right here is the number one place where people miss these problems. If you have to balance the atom that was oxidized or reduced, you need to adjust the number of electrons if necessary. And we'll show you what that means on one of our example problems. And now we move next into our sequence of balancing to balancing oxygen. We're always going to balance oxygen by adding water, H2O, because again, as I mentioned, these are reactions occurring within aqueous solution. So there's water present, and we can therefore balance oxygen by adding water. Our next step is to balance hydrogen by adding H positive ions, that is the hydrogen ion. Now, in doing so, it might seem illogical to do that in a basic solution because there are not a whole lot of hydrogen ions present in a basic solution. But don't worry about that. We have a next step here that accounts for that. If the solution is basic, we're going to add an equal amount of hydroxides to both sides of the equation, equivalent to the number of hydrogen we added previously in the start of step 6. And when we do the basic example, you'll see why that works out as an accounting tool. At that point, we're going to combine any hydrogen and hydroxide ions to make water, balance any remaining atoms, and then last but not least, the last thing that we balance in our sequence of balancing is the number of electrons. Now, because the electrons are produced via the oxidation and consumed via the reduction, they have to balance out because, again, you can't just have a reaction which is an infinite source of more electrons. So electrons, again, are a conserved particle in these reactions, which means we're going to balance these by multiplying the half reactions by whole number integers to find the least common multiple of electrons between the oxidation step and the reduction step. And then we move on to cleanup. We're just going to combine our half reactions, cancel out any like terms, and then check our work by checking for conservation, both of the number of atoms on both sides and of charge. So with those steps, I would encourage you as we do these practice problems that you jot them down into your notes and use them for your first couple of examples. And then after you get confident in the process, start to try to move away from relying on this sequence of steps here. Because again, on the actual AP test, you will not get a nice list of 11 steps. You're going to have to be able to produce this on your own. So try them first with the steps and then take them away for the ones after you get comfortable. We'll go ahead and try a couple examples in our next slides. All right, here we go. It comes to it. We're going to now balance a redox reaction. In particular, this reaction is occurring within an acidic solution. It's very important to note whether your redox reactions are being balanced in an acidic or a basic solution because it changes the sequence of steps that you are going to go through in order to make things balanced due to the different ions present, hydrogen ions in acidic solutions and hydroxide in basic solutions. So we need to watch out for those. So with our sequence of steps, we're going to go ahead and start at the very top. We're going to start with our reaction here, assigning oxidation numbers to all of the species present. So for our chemical reaction in which the bromide ion reacts to the permanganate ion, MnO4 1-, to form molecular bromine, Br2, and the manganese 2 ion, Mn2 +, let's go through using our oxidation step rules and figure out oxidation numbers. First one's easy. The bromide ion, Br-1, that's a monoatomic ion, which means its oxidation number is equal to its charge. So we got a -1 there. In the permanganate ion, the oxygen atom is in a -2 oxidation state, as it always is, unless we're in a peroxide. And then the sum of the oxidation numbers must equal the -1 overall charge, which means to balance out the 4 -2 oxygens, I needed one +7 manganese atom there to give me an overall sum of -1. So 4 -2s plus 7 gives me the -1 overall charge. Elemental bromine on the right side, every element in its native state has an oxidation number of 0, so we can assign that there. And then another monoatomic ion, easy on the right side, the manganese 2 ion has an oxidation number equal to its charge of +2. So we have now assigned our oxidation numbers. The next step is to go ahead and figure out what was oxidized and what was reduced. Now, starting off here, let's have a look first of all at the bromine. Our bromine started off with an oxidation number of -1 on the reactant side, and on the product side, it has an oxidation number of 0. So if we are going from an oxidation number of -1 to 0, we are becoming less negative, which means we must be losing an electron right there. So it looks to me like bromine here is being oxidized. Let's label that, showing here it has lost an electron. And in similar logic, if I start off with my manganese, which started at a +7 oxidation state, that +7 oxidation state is a very high oxidation state for manganese, which means this is something which is ripe to be reduced. And not surprisingly, on the right side here, I find manganese in a +2 oxidation state, which means we were reduced from a +7 down to a +2, and therefore manganese was the species reduced. It picked up 5 electrons to go from a +7 down to a +2. So I've now labeled my species oxidized and my species reduced. Following along with your notes again, next step is let's split into half reactions. I'm going to start with my oxidation half reaction first. So I'm only going to focus now on the species which are being oxidized. So on my reactant side here, I have the Br1 negative bromide ion. And on the product side, I have Br2. And again, I noted in my notes above here that bromine had lost an electron to go from a -1 to a 0. So I'm going to add that electron on the right-hand side, showing that that electron is being released from the species being oxidized here. And now for my reduction half reaction, we're starting off with our MnO4 negative, the permanganate ion, on the reactant side. On my product side, we're ending up at Mn2 positive. And again, we saw earlier that we said manganese picked up 5 electrons as it was reduced from a +7 down to a +2. So let's put those 5 electrons now on the reactant side, showing them being picked up by the permanganate ion there. So I now have half reactions, and these half reactions are certainly not balanced. So I now move into my sequence of balancing. And again, remember here, it's very, very important that we consider the order in which this sequence of balancing occurs. So starting off with the sequence of balancing, we always balance the atoms oxidized or reduced first. In my oxidation half step, that means bromine. So on the right-hand side, I've got 2 bromines, left-hand side I have 1, which means I need a 2 as a coefficient for my bromide ion. And again, on the previous slide, I had you star as a really important thing to watch out for here, that there is a place where people miss this problem, and that is right here. Recognize that bromine is going from an oxidation state of -1 down to a 0, but as I just balanced bromine there, I'm not doing that to 1 bromine atom, I'm doing it to 2. Which means for 2 bromine atoms, each to be oxidized from a -1 to a 0 charge, that implies, therefore, I have not given up 1 electron, I have given up a total of 2. So we need to adjust those electrons as necessary in our oxidation step. Now, happily for me, now that I've taken care of that, in my reduction step, manganese came already balanced. There's 1 on both sides, so I don't have anything to worry about right there. So we can move on within our sequence of balancing. After the atoms oxidized or reduced, we next balance oxygen. And we always balance oxygen by adding water. There is no oxygen in my oxidation step, but in my reduction half step there, I have, looks like 4 oxygens on the left-hand side, which means I'm going to balance that out by throwing 4 waters on the right-hand side of this chemical equation. So I've balanced oxygen by adding water. Next in the sequence of balancing comes hydrogen. This is an acidic solution, and as such, I'm going to balance hydrogen by adding H positive. I have 4 waters on the right-hand side of my manganese half step there for the reduction. So I need, therefore, 8 H positive ions on the left-hand side to balance out the number of hydrogens on each side. And again, this seems like I'm just cheating by pulling hydrogens out of nowhere, but remember, this is occurring within an acidic aqueous solution, which means hydrogen ions are a species which is present in concentration within this aqueous solution. So it's totally legitimate as a thing to do. So we've balanced the hydrogens by adding H positive ions. Because I'm in an acidic solution, I don't need to worry about that next little step we gave you about basic solutions. So we can just check and see, is there anything else in terms of atoms that need balancing? It looks to me like everything is checking out right now, which means the only thing that remains now in order to be balanced are my electrons. In my oxidation half step, we have 2 electrons being produced, but in the reduction half step, I have 5 electrons being consumed. Now, in order to make that work out, I'm going to have to essentially multiply each of those half steps by some integers to find the least common multiple of my number of electrons so that the number of electrons produced in the oxidation equals the number of electrons consumed in the reduction. So I'm just going to essentially cross multiply here. I'm going to multiply my oxidation half step by a factor of 5 and my reduction half step by a factor of 2. And again, that's going to get applied to all the species present in each of those half steps. And as I do that, I'm now going to go ahead and multiply those out, distribute that 5 and the 2, and simultaneously, I'm going to go through also and combine my oxidation half step with my reduction half step into one complete reaction. So, starting off, multiplying out here from my oxidation step, I have 5 times 2 bromines, 5 times 2 bromides, which gives me a total of 10 Br negative ions. Plus, from my reduction half step, I have 2 times 8 hydrogen ions, which gives me 16 H positive ions, plus 2 times the 5 electrons, which is 10 electrons, plus 2 MnO4 negative permanganate ions. So that's all the stuff, both in the oxidation and reduction steps, on the reactant side of my equations. Now on the product side, again distributing from my oxidation step, I have 5 Br2 molecules, plus 5 times 2 is 10 electrons, plus from my reduction step, distributing the 2 Mn2 positive ions, plus 2 times 4, which is 8 water molecules, 8 H2O. And all that now remains is to go through and to cancel out like species, which in this instance is only those 10 electrons. And if ever you find yourself in a position where your electrons are not canceling out, something has gone horribly wrong and you need to go back. And unfortunately here, sometimes it's easier to go all the way back to start and rework it from scratch rather than going back and trying to figure out what went wrong along the way. But I'm pretty confident here, I'm feeling pretty good. I think we can move on. So we'll rewrite our equation here without those 10 electrons on both sides, which gives me 10 Br negative plus 16 H positive plus 2 MnO4 1 negative forms 5 Br2 plus 2 Mn2 positive plus 8 H2O. So I've got an equation. Let's check to see if it actually balanced. On the left-hand side for bromine, I have 10 bromines. Right-hand side, 5 times 2 is 10 bromines. 16 hydrogens on the left. 8 times 2 is 16 hydrogens on the right. 2 manganese on the left, 2 manganese on the right. 2 times 4 is 8 oxygens on the left, 8 oxygens on the right. And then remember, we're balancing both atoms and charge, which means on the left-hand side, I have 10 bromides, each with a -1 charge, so that's a total of -10, plus 16 1 positive hydrogen ions, so -10 plus 16 is a +6, and then 2 -1 permanganate ions brings me from a +6 down to a +4. So the sum of all the charges on the left-hand side is +4. Right-hand side, a little easier here. I have 2 manganese 2 ions. For 2 times +2 is +4. So atoms balance, charge balances. This here is a balanced redox reaction. Hooray! We'll move on next and try a basic solution reaction. All right, for our last example here, we're going to do a basic solution redox reaction, and this one is a doozy, so get ready. The sequence of steps is the exact same. Follow the sequence of steps and trust that it will get you to the correct answer in the end. even when things get a little weird along the way here. So in this reaction, we have the iodide ion, I1 negative, reacting to the hypochlorite ion, ClO1 negative, to form the triiodide ion, that is I3 1 negative, and the chloride ion, Cl1 negative. And as we follow our steps for redox reactions, we remember the very first thing we need to do is to start by assigning oxidation numbers. So starting off on the left-hand side there, we've got the monoatomic iodide ion, which means its charge is equal to its oxidation state of -1. We then have the hypochlorite ion, which contains oxygen. We'll go ahead and give the oxygen, as always, a -2, which means to make our sum of oxidation states equal the overall -1 charge on this ion, we need to have chlorine in a +1 oxidation state there. And here's where things are going to get weird. We have the triiodide ion, I3 -1. And remember, our rule said that the sum of the oxidation states of all of the atoms present in a species must equal the overall charge on that species. That means the sum of the oxidation states of 3 iodines here must equal -1, which logically speaking then means the oxidation state of iodine must be here -1/3. And I know what you're thinking right now, that is nonsense, you can't have a fractional oxidation state. And my response to that is, oh, absolutely you can. Because remember, oxidation states are really just a tool, an accounting tool to help us keep track of electrons here. So obviously there's no such thing as a third of an electron, but these are not electrons, this is an accounting tool and nothing more than that. So don't worry about it. If you get a fractional oxidation state, it can still work out, as you'll see in this problem. And then over on the right-hand side, easier one here, we've got the chloride ion, monoatomic ion, oxidation state equal to its charge of -1. So we've assigned our oxidation states. Let's now go ahead and figure out what was oxidized and what was reduced. We'll deal with the reduction first because that's friendlier. Chlorine is going from a +1 down to a -1, which means to go from a +1 to a -1, chlorine here must be gaining 2 electrons. That chlorine is being reduced. And for my oxidation, have a look at my iodine, starting off at a -1 on the reactant side and ending up at a -1/3 on the product side. To go from -1 to -1/3, that means that iodine is becoming less negative by losing, it looks like here, 2/3 of an electron. Now again, don't panic that makes no sense right now. It's going to work its way out in the sequence of steps. So we're going to say here, iodine was oxidized, it lost 2/3 of an electron. So we've got our oxidation numbers assigned. Let's now go ahead and split into half reactions. Starting off with the iodine, we have, let's see here, for my oxidation step, I1 negative on the reactant side. On the product side, the triiodide, I3 1 negative. And we're going to go ahead and say that we lost there 2/3 of an electron. And again, we're going to put that on our product side. So we've got our oxidation half step written. Now for my reduction half step. I started off with the hypochlorite ion, ClO1 negative on my reactant side. I ended up with a chloride ion, Cl1 negative on the product side. And to make that happen, we said chlorine picked up 2 electrons. So let's put those 2 electrons on the reactant side to make sure we get them in the proper place. So we've now written our half reactions. And from here, we move on to our sequence of balancing. Now, remember the order in which we balance things is very important here. We're always going to start with the atoms which were oxidized or reduced. My atom oxidized was the iodine. So I have one iodine on the left side. I have 3 on the right. So I'm going to throw a 3 as a coefficient there on the left side. And again, alarm bells going off right now. I just changed the number of an atom being oxidized or reduced, which means I have to adjust my number of electrons. And here's where the world is going to look a little bit better now. Because I multiplied the iodines by a factor of 3 that are present here, if each of the iodines we said was losing 2/3 of an electron, I'm essentially then just going to multiply that by 3 if it's happening to 3 iodines, which means 3 times 2/3, there are a total of 2 electrons then given up as those 3 iodide ions are reduced to 1 I3 triiodide. And that all of a sudden makes more logical sense. I'm no longer dealing now with fractional electrons. All right, so we've balanced our oxidation half step. It looks friendlier now. Let's go ahead and look at the reduction. Atom being reduced was chlorine. I've got equal numbers on both sides. I'm good to go there. Next in my sequence of balancing is the oxygen. I've got nothing in my oxidation step, but in my reduction, I've got the ClO ion on my reactant side, which means I need to throw 1 water H2O on my product side over there. So I've balanced oxygen by adding water. Next in the sequence of steps is to balance hydrogen by adding hydrogen ions. And again, you're going to panic here because we're in basic solution. You don't think we should be balancing with hydrogen ions, and you've got a point there. But again, trust the sequence of steps. It's going to work out for a reason you'll see momentarily. So I've got H2O on the product side of my reduction step there, which means I need to put 2 hydrogens on the reactant side over there, 2 H positive ions. Now, remember, in our sequence of steps, there was a next step there that said, if you are dealing with a basic solution, the next thing we do is to add an equal number of hydroxide ions to both sides of my equation, equivalent to the number of hydrogens that I just added. So because I just added 2 hydrogen ions to my reactant side, I'm now going to add 2 hydroxide ions to both the reactant and the product side. And as I do that, I recognize that on my reactant side, I now have 2 OH negative ions plus 2 H positive ions, and really OH negative and H positive make water. So I have 2 H2Os right there. And now all of a sudden it makes logical sense why I just did that, because I have previously balanced oxygen by adding water. And I didn't want to just then add hydroxide ions in order to balance my hydrogens, because if I did that, I would unbalance my oxygens again, which I just previously balanced. So you'll see in the steps that I just performed there, the act of adding both hydrogen and hydroxide has the net effect of adding hydroxide ions to one side or the other, while simultaneously keeping my oxygens balanced by essentially adding more water at the same time. So again, I've got a little accounting trick there that helps me to keep track of my hydrogens and oxygens by balancing here with hydroxide within the basic solution. So that all seems like it's going to work out. So I have now balanced my hydrogens. I need to check to see if there's anything else in terms of atoms that need balancing, but it doesn't look like it to me. The only thing left that remains is, again, balancing electrons, but happily for me, I'm no longer dealing with that fractional electron mess. 2 electrons are being produced in my oxidation step, 2 are being consumed in the reduction, which means I am good to go. I don't need to worry about any multiplication of my half steps there. So all that then remains is to combine my half steps. And I will do so starting off with the reactant side of the oxidation half step. I have 3 I negative iodide ions, plus from my reduction step, 2 water molecules that I made by combining my hydrogen hydroxides, plus 2 electrons, plus the hypochlorite ion, ClO1 negative. And then on my product side, from the oxidation, I have I3 negative, that triiodide ion, plus 2 electrons, plus from my reduction half step, I have the Cl1 negative chloride ion, plus water, H2O, plus 2 hydroxide ions, OH negative. And now I can do some cancellation here and simplify my equation. I notice that I, again, have canceled out my 2 electrons, which is good. If those don't cancel, something went wrong, so we're good there. And then I can also simplify here, recognizing that I've got 2 waters on the reactant side and only 1 on the product side. Let's cancel out 1 water from both sides. And I'll rewrite my equation now, which gives me 3I1 negative plus H2O plus ClO1 negative forms on the product side I3 negative plus Cl1 negative plus 2 OH negative. And last but not least, let's go ahead and check to make sure we have balanced both atoms and charge. I've got on my left-hand side there 3 iodines, right-hand side 3 iodines, left side 2 hydrogens, right side 2 hydrogens, left side, careful here, 2 oxygens, one in the water and one in the hypochlorite ion. And then right side, 2 oxygens in my hydroxide ion. And then I've got 1 chlorine on both sides. It looks like atoms are balanced. And then last but not least, charge. I've got 3 I negative ions for a total of -3, plus the hypochlorite ion with 1 more -1. So that's a total of -4 on the left-hand side. And on the product side there, I have I31 negative, Cl1 negative, so that's -1, and a -1 is -2. And then 2 hydroxide ions, each which is -1. -2 plus that -2 is therefore -4. So I have a -4 charge on both sides. That means atoms are balanced, charge is balanced. We have now a balanced chemical equation. And that was a joy. Thanks for playing along with me here, guys. And good luck trying these on your own. Make sure that as you do these on your own, that you start by using your sequence of steps. Use that as a crutch until you feel confident. And then once you've got the sequence memorized, you can move on and try them on your own. Good luck. Enjoy.